Okay, morning everybody. Hope you're doing well today. So we are going to continue to discuss uh, slope, and we are still in Chapter 3, Section 3. And what we're going to talk about today is a little bit of terminology, and then I'm going to show you some examples of how to find slope, um, not necessarily using the formula for slope like I've showed you before, but maybe from a table or from a graph, something like that. So first of all, it says vocabulary, rate of change, a ratio that describes how much one quantity changes, and that's the word that we want to put in there, changes with respect to a change in another quantity. So you have to excuse my writing. It's as good as it can be given the circumstances, but that word should be changes. So you can see right here it says rate of change, and the rate of change is another fancy word for slope, and that is simply the change in y divided by the change in x. So it's always the change in y over the change in x. So if we look at this table that we have for this first example, you can see that this is my x's right there. Let me get a different color. It's easier to see. This is my x's and those are my y's. So we always want to figure out what the change in the y is first. Now, the way we find the change in y is very simple. We subtract it. So if I look at these numbers, and I'm going to zoom in here a little bit on this, but if I want to know in these two numbers right here, how far, whoops, I don't want to use that. Let's use this. How far apart are those two numbers? We're going to simply do 156 minus 78. And when I do that, I get a total of 78. So what that means right here is in the y value, I added 78 to turn into 156. Now right here, I need to figure out how far those two numbers are apart. So I have 234 minus 156. And when I do 234 minus 156, lo and behold, I get 78 again. And so what I want you to see here is how we went from this number to this number to this number is they are adding 78 each time. Now it's important that that amount, whether it be adding or subtracting, it's important that amount is consistent. So it has to be the same amount each time between the y values. And the same is going to hold true for the x values. So over here, you can see we went from 2 to 4. Well, that was adding 2, right? We could figure that one out without having to actually subtract the numbers. And then I went from here, I went from 4 to 6, and that was also adding 2. So now we have these two quantities, right? We have the change in y, and then we have the change in x. So in order to calculate our slope, it's as simple as delta y over delta x. And that's going to be plus 78 over plus 2. Now that will reduce to 39 over 1 in simplest terms. But the slope in this case is the cost is going up $39 for every one game. And that's how you calculate your slope from a table. Let's try another one. So this table says the number of floor tiles and then the area of tiled surface. So as we get more and more tiles, you can see the tiles are increasing. The surface area that is tiled is also increasing. But we need to figure out the difference again. So how much was it from here to here? And then how much was it from here to here? And it's really easy. You subtract the numbers. So when I do 96 minus 48, I get 48. So this was plus 48. Now I need to go from 144 to 96. So I need to do 144 minus 96. And when I do that, I get 48 again. So it was another increase of 48. Okay. Now over here from 3 to 6, that was plus 3. And from 6 to 9, that was plus 3. So you can see now we have a consistent amount that the y's are changing by, and we have a consistent amount the x's are changing by. And so to get our slope, that's going to be our change in y over our change in x, which is 48 over 3. Now in simplest terms, both of those can be divided by 3. So you would get 16 over 1, which means the area tiled, this is the surface area, this is the number of tiles. So you can see that the area increases by 16 inches squared every time we add a tile. Now, this one we want to find the rate of change, but we want to find it from a graph instead of a table. The graphs are actually easier in my opinion because we are still trying to figure out the change in y over the change in x. And so what we simply do is pick a point, and we're going to start with this point. The reason why we're starting with this point is that point is at a perfect grid intersection. And we're going to go to the next point, which is up here, that is also in a perfect grid intersection. And we're going to count. That's it. So we always want to figure out how far up or down first, then how far left and right. And so in this case, I'm starting at 4, and I'm going up there to 10. So counting from 4 to 10, it is 2, 4, 6. So the change in y is 6. We went up 6. And now I'm going to change over to blue just so you can see. From here to here, we're counting by ones. Be very careful. Down there, it goes 2, 3, 4. So it goes from 2 to 3 to 4. So in that case, it's 2. So this distance was 2. Now this one's a little bit trickier of a problem because the scaling is not the same. And what I'm talking about is if you look at the bottom numbers, they count 1, 2, 3, 4, 5. But if you look at the side numbers, they count by twos, 2, 4, 6, 8. So you got to be really careful when you're scaling that you do count correctly. But in this case, we went up to from 4 to 10, so that was an increase of 6, and then we went over from 2 to 4, which was an increase of 2. So you can see my slope is 6 over 2, and that will reduce, they're both divisible by 2, that turns into 3 over 1. Now this one asks us to compare rates of change. So comparing rates of change, it says the graph shows the number of people who visited US theme parks in recent years. And so you can see from 2000 to 2002, it was fairly steep. And then it wasn't nearly as steep from 2002 to 2004. And then when we go from 2004 to 2006, it got really steep, even steeper than the first 2 years. And so what they would want us to determine is which graph or which line is the steepest and how steep it is. So if I look here, you can see each year is +2, right? So that's my change in x. So this is my delta x. Now I need to figure out my change in y's by subtracting these 3 pairs of numbers like that. Okay, so if you look at the first pairs of numbers, 317 to 324, that is an increase of 7. And remember, this is in millions. So there was an increase of 7 million. Now, from 2002 to 2004, there was only an increase of 1 million. And then from 2004 to 2006, there was an increase of 10 million. And so now we've got to come up with the slope of each one of these lines. So again, you're finding the change in x and the change in y first, and then you write the slope. And you can see the change in x's are always consistent. It's every 2 years. So what we end up having is 7 over 2, right? So 7 million over 2 years. The next one is 1 million over 2 years. And then the last one is 10 million over 2 years. And that's how you come up with your slope. Now, the last thing I'm going to show you is whether a function is linear. Okay. Now, how do you know whether something is linear? Well, it has what we say a constant rate of change. And what the constant rate of change is, and this is what I was explaining in the very first problem, you've got to have the same amount changing in the x and the y. in order for it to be linear. So if you look at the y values here are decreasing by 4 for the first one. When you go from 5 to 1, that's subtracting 4. Now when I go from 1 to -4, that is subtracting by 5. And then the last one, when I go from -4 to -10, that is subtracting by 6. And so we can already see that this is not going to be a linear set of data because the y values are not the same. But let's look at the x's. Over here, I'm adding 8 to go from -10 to -2. And then from -2 to 6, that's also adding 8. And then from 6 to 14, that also added 8. So you can see the x values are consistent, right? But because the y values are not the same, this is not linear. And so the answer would be no. Y values change differently. So in order for the function to be linear, it has to change the same across the y's and the same across the x's. I'll give you another example. So let's look at this one, see if it's linear. So if I look at the x's, each one of these is +1 for the first two. And then this one is +2 and then +1. And that's okay. You can go overcome that, which I'll show you here in a second. Now this one is +4. This is +4. This one's +4. And this one is +4. So what you can see is now the y's are consistent, but the x's are not consistent. And so when I write the slope, it would be 4/1, 4/1, 4/2, 4/1. That's not consistent. So this is no as well. Okay, now the last one. If I look at here, I'm subtracting 3 each time. And over here, I'm adding 5 each time. And so as you can see, all the y's are the same. All the x's are the same. So yes, this is linear. And it's because the y's and the x's are changing by the same amount. So there you go. I hope that made sense. As always, if you have any questions, feel free to email me. Have a great day.